be available. We'll have a half an hour of discussion at the end of this period. In order to move right along, Craig Idso, PhD in physical sciences and a specialist in carbon sequestration technology and the study of carbon. God, don't we love carbon? You know, most people don't realize, I've got 4 horses and 4 dogs, and I was just thinking about the carbon imprint that I must put on some satellite. Craig, are you ready? Craig Idso.
It's sliding. Has to stay there. Good morning. One of the long recognized consequences of the ongoing rise in the air's CO2 content is CO2-induced global warming, which has been predicted to pose a number of problems for both natural and managed ecosystems in the years ahead. Of newer concern in this regard are the effects that elevated CO2 concentrations may have on coral reefs. It has been suggested, for example, that CO2-induced global warming will do great damage to corals by magnifying the intensity, frequency, and duration of a number of environmental stresses to which they are exposed. The predicted consequences of such phenomena include ever more cases of coral disease, bleaching, and death. Increases in the atmosphere's CO2 content have also been postulated to possess the potential to harm coral reefs directly, by inducing changes in ocean water chemistry that can lead to reductions in the calcium carbonate saturation state of seawater. It has been predicted that elevated levels of atmospheric CO2 may reduce rates of coral calcification, possibly leading to slower growing and therefore weaker coral skeletons, and in some cases, even death. Because of these many concerns and the logical desire of individuals and governments to do something about what they perceive to be serious threats to the well-being of these incomparable underwater ecosystems, it is important to have a correct understanding of the scientific basis for the problems that have been predicted. Consequently, in an effort to determine if the ongoing rise in the air's CO2 content really is the threat it is made out to be, our organization has continuously reviewed the scientific literature on carbon dioxide and coral reefs for well over a decade now. And in January of this year, we released a detailed report of our findings, the results of which I will present to you here today. We begin with a discussion of coral bleaching. Coral bleaching is a phenomenon that is characterized by a loss of color in certain reef-building corals that occurs when algal symbionts, or Zooxanthellae, living within the host corals are subjected to various stresses and expelled from them, resulting in a loss of photosynthetic pigments from the coral colony. Now, if the stress is mild or short in duration, the affected corals often recover and regain their normal complement of the Zooxanthellae. However, if the stress is prolonged or extreme, the corals eventually die, being deprived of their primary food source. One of the most frequently cited causes of coral bleaching is anomalously high seawater temperature, but the story is much more complicated than that. Additional research has identified other causes of coral bleaching, including anomalously low seawater temperature, prolonged exposure to high levels of solar irradiance, a combined solar radiation temperature stress synergism, reduced salinity, bacterial infections, increased sedimentation, and exposure to toxicants. Considering these many local and global threats to the health of Earth's coral reefs, it is only logical to wonder why reefs persist at all, and sometimes even flourish. To what do they owe their amazing resilience? And how do they meet the physiological challenges presented by the combination of high light intensities and water temperatures that many climate alarmists consider to be the primary cause of mass coral bleaching? The answer, in a word, is adaptation. A simple example of adaptation to the stress imposed by high solar irradiance comes from studies of corals that exhibit a zonation of their symbiont taxa with depth, where symbiont algae that are less tolerant of intense solar radiation grow on corals at greater depths below the ocean's surface. It has also been demonstrated that coral Zooxanthellae possess a number of light-quenching mechanisms that can be employed to reduce the negative impacts of excess light. Both the coral host and its symbionts also have the capacity to produce amino acids that act as natural sunscreens, and they can regulate their enzyme activities to enhance internal scavenging systems that remove noxious oxygen radicals produced in coral tissues as a result of high light intensities. With respect to thermal adaptation, in a paper published just last year, Maynard et al. Analyzed the severity of bleaching of 3 genera of corals that bleached in 1998 and again in 2002 on Australia's Great Barrier Reef. Their results indicated that the amount of accumulated thermal stress in 2002 was more than double that in 1998, while the average surface irradiance was 16% higher. Nevertheless, the severity of bleaching in 2002 was 30 to 100% lower than what it was in 1998. What is more, the 2 corals most susceptible to bleaching as a result of thermal stress in 1998 exhibited the least bleaching in 2002. In further discussing their findings, Maynard et al. Say they are consistent with the findings of previous studies that have documented increases in thermal tolerance between bleaching events in the Galapagos Islands, the Gulf of Chiriquí, the Gulf of Panama, the Andaman Sea, and on Costa Rican reefs. In addition, they say there is emerging evidence of high genetic structure within coral species, which suggests in their words that the capacity for adaptation could be greater than is currently recognized. Indeed, as stated by another team of independent researchers, on the basis of the present knowledge of genetic variation in performance traits and species capacity for evolutionary response, it can be concluded that evolutionary change will often occur concomitantly with changes in climate as well as other environmental changes. Consequently, it can be appreciated that if global warming were to begin again, remember it's been in abeyance for about the last decade, it need not spell the end for Earth's highly adaptable corals. Another adaptive mechanism that corals have developed is to replace the Zooxanthellae expelled by the coral host during a stress-induced bleaching episode by one or more varieties of Zooxanthellae that are more tolerant of the stress, a phenomenon known as symbiont shuffling. Another mechanism is to produce heat shock proteins that help repair heat-damaged constituents of their bodies. A third means of survival consists of corals rearranging their bacterial populations in a process akin to symbiont shuffling, which adaptive mechanism, to quote one research team, gives corals an enormous genetic potential to adapt rapidly to changing environmental conditions. In fact, they say it is not unreasonable to predict that under appropriate selection conditions, this change could take place in weeks rather than decades required for classical Darwinian mutation and selection. Whatever the favored mechanism or group of mechanisms, it is clear that coral reefs have been able to successfully adapt to various environmental stresses ever since bursting upon the scene some 450 million years ago. And there is no compelling reason to believe they will not continue to survive throughout the years ahead. Faced with these facts and recognizing that coral bleaching is turning out not to be the catastrophic threat they initially claimed it was, climate alarmists have seized upon another boogeyman of sorts, which they contend has a far greater potential to destroy Earth's coral reefs. And this new phantom is ocean acidification. So what's the story here? According to the acidification hypothesis, the global increase in the atmosphere's CO2 content has the potential to harm coral reefs directly by inducing changes in ocean water chemistry as the world's oceans absorb ever more quantities of CO2, which absorption in turn is postulated to reduce the calcium carbonate saturation state of seawater, thereby lowering rates of coral calcification. The end result of these processes is believed to be slower growing and therefore weaker coral skeletons, and in some cases even death. But is there any real-world evidence that can be cited in support of these claims? The acidification alarmists certainly make it appear such is the case, but the scientific literature reveals nothing of substance in this regard. In fact, it seems to suggest just the opposite. Consider, for example, observations of coral calcification rates over the past century, during which time ocean temperatures and atmospheric CO2 concentrations both increased. In a study of colonies of Porites coral scattered throughout Australia's Great Barrier Reef, it was determined that between the two 50-year periods, 1880 through 1929, and 1930 through 1979, there was an approximate 4% increase in calcification rate. Additional studies from the French Polynesian island of Morea, the Gulf of Mexico, and the Caribbean Sea reveal an even higher modern-day increase of calcification of around 8%, which results are radically different from the 6 to 14% decrease suggested to result from CO2-induced ocean acidification during this time period by a study based primarily upon theoretical calculations. But perhaps even more stunning was the additional discovery from the Australian study that between the two 20-year periods, 1903 through 1922 and 1979 through 1998, there was a warming-induced increase in coral calcification of about 12% in the central Great Barrier Reef, about 20% in the southern Great Barrier Reef, and as much as 50% to the south of the Great Barrier Reef. After pooling these data with data from still other species of coral living off the coasts of Belize, the U.S. Virgin Islands, and the Netherlands Antilles, an all-inclusive relationship of 0.45 grams of calcification per centimeter squared per year for each 1 degree Celsius increase in annual average sea surface temperature was obtained. In one additional study that involves a much longer period of time, another research team documented the growth rates of long-dead quaternary corals, after which they compared them to the growth rates of present-day corals of the same genre living in the same part of Indonesia. This work revealed that the quaternary corals grew in a comparable environment to the modern reefs, except, of course, for the air's CO2 concentration, which is currently higher than it has been at any other time throughout the entire quaternary, which spans the past 1.8 million years. Most interestingly, their measurements indicated that the radial growth rates of the modern corals was 31% greater than those of their ancient predecessors in the case of Porites species and 34% greater in the case of Phovites species. To these papers, we could also add many others that also depict increasing rates of coral calcification in the face of rising temperatures and atmospheric CO2 concentrations. As for why this is the way Earth's corals respond, one research group has said that observed increases in coral reef calcification with ocean warming are most likely due to an enhancement in coral metabolism and/or increases in photosynthetic rates of their symbiotic algae. as we have consistently stated on our website when noting over and over that coral calcification is a biologically driven process that can overcome physical chemical limitations, which in the absence of life would appear to be insurmountable. It is also important to note that the same phenomenon that powers the twin processes of coral calcification and phytoplanktonic growth, namely photosynthesis, tends to increase the pH of marine waters and make them less acidic, or more properly, more basic. And this phenomenon has been shown to have the ability to dramatically increase the pH of the world's marine bays, lagoons, and tidal pools, as well as significantly enhance the surface water's pH of oceanic areas as large as the North Sea. In any event, the net impact of 20th century increases in atmospheric CO2 and temperature has not been anywhere near as catastrophically disruptive to Earth's corals as climate alarmists suggest it should have been. Quite to the contrary, the temperature and CO2 increases appear not to have been hurtful at all. In fact, they actually appear to have been helpful. But what about other calcifying marine organisms? Have they been harmed in any way? Some insight into this subject was recently provided by an international team of 13 researchers who bubbled air of a number of different atmospheric CO2 concentrations through culture media containing the phytoplanktonic coccolithophore species Emiliania huxleyi, while determining the amounts of particulate organic and inorganic carbon they produced. In addition, they determined the real-world change in average coccolithophore mass over the past 220 years based on data obtained from a sediment core in the subpolar North Atlantic Ocean, over which period of time, I might add, the atmosphere's CO2 concentration rose by approximately 90 parts per million, and the Earth emerged from the frigid depths of the Little Ice Age to experience those supposedly unprecedented high temperatures of the current warm period. So what did they find? What they found was an approximate doubling of both particulate organic and inorganic carbon from the culture media in equilibrium with air of today's CO2 concentration to the culture media in equilibrium with the air enriched to 750 parts per million CO2. In addition, they say the field evidence they obtained from the deep ocean sediment core they studied is consistent with the laboratory conclusions and indicates, as shown in the figure, that over the past 220 years, there has been a 40% increase in average coccolith mass. Now, similar results have also been reported by a second independent team of scientists who grew Emiliania huxleyi coccoliths in semi-continuous culture media at low and high light intensities, low and high temperatures, and low and high CO2 concentrations. This work revealed that in the low light environment, the maximum photosynthetic rate was lowest in the low temperature, low CO2, or ambient treatment, but was increased by 55% in the elevated temperature treatment and by 95% in the elevated CO2 treatment. Well, in the high temperature, high CO2 treatment, it was increased by a whopping 150%. Likewise, in the highlight environment, there were maximum photosynthetic rate increases of 58%, 67%, and 92% for the elevated temperature alone, elevated CO2 alone, and combined elevated temperature and CO2 treatments, respectively. Consequently, the researchers concluded that future trends of CO2 enrichment, sea surface warming, and exposure to higher mean irradiances from intensified stratification will have a large influence on the growth of Emiliania huxleyi. And of course, that large influence will be positive and tremendously so. Because of time constraints, I must now conclude my presentation. Before doing so, however, I'd like to invite each of you to visit our website, www.co2science.org, where you can read our seminal report, CO2, Global Warming, and Coral Reefs, Prospects for the Future, which gives a much expanded view of what I presented to you here today. And to summarize that view, although climate alarmists have postulated that the ongoing rise in the air's CO2 content will harm coral reefs and other calcifying organisms, both directly and indirectly, neither increases in temperature nor increases in atmospheric CO2 concentration, nor increases in both of them together have had any lasting ill effects on the important processes of calcification and growth in marine organisms. In fact, out in the real world of nature, these processes have actually been enhanced by the supposedly unprecedented concomitant increases in these twin evils of the radical environmentalist movement. If there is a lesson to be learned from the materials I've discussed today, it is that policymakers should be paying much more attention to real-world observations than to theoretical projections. Far too many predictions of CO2-induced catastrophes are treated by many of them as sure to occur, when real-world observations show these doomsday scenarios to be highly unlikely or even virtual impossibilities. The phenomena of CO2-induced coral bleaching and ocean acidification are no different. We have got to realize that atmospheric CO2 concentrations are not the bane of the biosphere, but an invaluable boon to the planet's many life forms. Thank you.